If you take a sample of benzaldehyde and drop it into a beaker of concentrated base, something curious happens. Usually, when we think of aldehydes in basic conditions, we expect them to start attacking each other to form long chains, the classic aldol reaction. But look closely at this molecule. It lacks a very specific feature, alpha hydrogens. Without those acidic protons to pluck away, the standard reaction path is blocked. So, what does the molecule do instead? It enters a sort of molecular pact. One molecule sacrifices itself to save another. This is the Cannizaro reaction, a beautiful example of a biological-style disproportionation happening in a simple test tube. Let's visualize the landscape. We have our aldehyde sitting there with its polar carbon-oxygen double bond. Because there are no alpha hydrogens, the hydroxide ion, our base, has only one target. It's attracted to the partially positive charge on the carbonyl carbon. As you can see here, the hydroxide attacks. This pushes the electrons from the double bond up onto the oxygen, creating what we call a tetrahedral intermediate. At this stage, the oxygen is unstable. It's carrying a full negative charge, and it wants to collapse back down to reform that stable double bond. But here is where the unique aha moment of the Cannizaro reaction occurs. As that oxygen pushes its electrons back down to reform the carbonyl, something has to leave. Normally, the hydroxide would just pop right back off and we'd be back where we started. But in this specific environment, the carbon-hydrogen bond breaks instead. The hydrogen leaves, taking both electrons with it. This is a hydride shift. We don't often see hydrogen leaving with its electrons like this, but look at where it's going. It's being handed off directly to a neighboring aldehyde molecule. Notice how this single move transforms both players simultaneously. The first molecule, which lost the hydride, has now become a carboxylic acid. It has been oxidized. The second molecule, which accepted the hydride, has become an alkoxide. It has been reduced. One molecule climbs the oxidation ladder while the other steps down. But we aren't quite finished. Now we have a strong acid and a very strong base sitting right next to each other. In a final, lightning-fast exchange, the carboxylic acid gives up its proton to the alkoxide. Looking at our final beaker, what do we have? We started with two identical aldehydes. We ended with one molecule of alcohol and one carboxylate salt. It's an elegant solution to a chemical dead end. When a molecule finds itself in a harsh environment with no standard way to react, it finds balance through disparity. The Cannizaro reaction reminds us that in chemistry, as in life, sometimes the only way for a group to move forward is for its members to take on two completely different roles. One gives, one takes, and the system finds its equilibrium.